Welcome! In this session, we'll dive into LeetCode problem number 795, titled Number of Subarrays with Bounded Maximum. We'll explore how to efficiently count subarrays that meet specific constraints and highlight the key concepts involved. Let's get started. In this problem, we are tasked with finding the number of valid subarrays within a given array nums. A subarray is simply a contiguous sequence of elements from the array. To determine if a subarray is valid, we check if its maximum value lies within the given bounds left and right, inclusive. So, the maximum value of the subarray must satisfy the condition left equals max, subarray, equals right. Our goal is to count how many such valid subarrays exist in the input array. The constraints ensure that the length of nums can be up to 100,000, and individual elements can be as large as 1 million, so the solution must be efficient. The input consists of the array nums, and the integers left and right, while the output is a single integer representing the count of valid subarrays. To understand the problem better, let's look at an example. Suppose nums is 2, 1, 4, 3, with left equal to 2 and right equal to 3. The output here is 3 because there are 3 valid subarrays. These are 2, where the maximum is 2, 2, 1, where the maximum remains 2, and 3, where the maximum is 3. All of these maximum values lie within the range 2, 3, so they are valid. On the other hand, subarrays like 4 or 2, 1, 4 are invalid because their maximum values exceed the upper bound of 3. Now, let's examine another example. Here, nums is 2, 9, 2, 5, 6, with left equal to 2 and right equal to 8. The output in this case is 7 because there are 7 valid subarrays. We start with 2, which has a maximum of 2, followed by 2, again later in the array. Subarrays like 5 and 6 are also valid since their maximum values, 5 and 6, respectively, fall within the range 2, 8. Larger subarrays like 5, 6 are still valid because their maximum value, 6, remains within bounds. However, subarrays such as 2, 9 are invalid because 9 is greater than the upper limit of 8. Additionally, let's look at a third example. Here, nums is 1, 4, 2, 1, with left equal to 1 and right equal to 3. The output here is 6. For this input, the valid subarrays include 1, where the maximum is 1, and smaller subarrays like 2 or 2, 1 later in the array, where the maximums are within bounds. However, subarrays like 1, 4 are invalid because the presence of 4 makes the maximum exceed the upper limit of 3. This example shows how we must carefully evaluate each subarray to ensure it satisfies the conditions. Finally, the problem comes with specific constraints and edge cases. The length of nums can go up to 100,000, so our solution must handle large inputs efficiently. Also, the values in nums can range from 0 to 1 million, which means we need to account for potentially large numbers during our calculations. Some edge cases to consider include when all elements in the array are outside the range defined by left and right. In such cases, the output would be 0 since no valid subarrays exist. Another important case is when the array has only one element. Here, we just check whether that single value satisfies the condition. Remember, subarrays must always be non-empty, and the constraints ensure that nums will never be empty, so there's no need to handle an empty array scenario. To tackle LeetCode problem number 795, our goal is to count the number of contiguous subarrays where the maximum value lies within a specified range, left, right. A straightforward approach is to use brute force, where we generate all possible subarrays and check if each satisfies the condition. This involves iterating through the array with nested loops, finding the maximum value of each subarray, and counting the valid ones. While this method is intuitive, it is computationally expensive, as calculating the maximum for every subarray can push the time complexity to O(n squared, or even O(n cubed, in some implementations. Despite its simplicity, this approach is not practical for large inputs due to its inefficiency. The brute force method, while straightforward, becomes infeasible for arrays with large sizes, such as when n reaches 10 to the power of 5. The repeated computation of maximum values for every subarray results in a steep time complexity, which makes it unsuited for competitive programming. To address this, a more efficient solution is to use the sliding window technique, also known as the two-pointer approach. Here, we avoid explicitly generating subarrays by dynamically maintaining a valid window as we traverse the array. If the current element exceeds right, the window is reset, as no subarray containing this element can be valid. If the current element falls within the range, left, right, we extend the window and calculate the number of valid subarrays ending at the current index. For elements less than left, we use the most recent valid window to extend our count. This approach reduces the need for repeated calculations and leverages the problem constraints to streamline the process. The sliding window technique is highly efficient due to its linear time complexity, O(n), as we only traverse the array once. It also has a space complexity of O(1), as no additional data structures are required. This makes it particularly well suited for large arrays. While the sliding window approach is intuitive and efficient, an alternative method involves using prefix sums for mathematical counting. This approach requires tracking the counts of valid subarrays using additional bookkeeping. While it also runs in O(n) time, the need for extra memory increases its space complexity to O(n). This added complexity and memory usage make it less favorable compared to the sliding window technique. Despite being a valid solution, the prefix sum method is less commonly employed due to its reduced clarity and simplicity. Among the considered approaches, the sliding window, or two-pointer, method is the clear choice due to its simplicity, efficiency, and minimal space requirements. It effectively handles the constraints of the problem, focusing on counting valid subarrays directly without the need for explicit generation or iteration. This drastically reduces the time complexity compared to brute force, making it ideal for competitive programming. While the prefix sum method is an alternative, its higher space usage and increased implementation complexity make it less appealing. The key insight here is recognizing that subarrays can be counted directly by utilizing their end indices, eliminating unnecessary overhead. This realization allows us to achieve a linear time complexity of O(n) and a constant space complexity of O(1), ensuring the solution is optimal for the given constraints. To solve the problem of counting subarrays with a bounded maximum, we first need to understand the constraints and the goal. The task is to find all contiguous subarrays where the maximum element lies between left and right, inclusive. A critical observation here is that any subarray where the maximum exceeds right is invalid, and subarrays where all elements are less than left don't contribute to the count. Instead of examining every possible subarray, which would be computationally expensive at O(n²), we can take advantage of a sliding window approach. By focusing on the position of the last invalid element, where an element exceeds right, we can efficiently calculate the number of valid subarrays ending at each index in linear time. Now let's break down the algorithm step by step. We begin by initializing a few key variables. The variable count will keep track of the total number of valid subarrays. Start will mark the beginning of the current valid subarray window, while last_invalid will hold the index of the most recent invalid element, which helps us identify where the current valid window starts. Additionally, valid_count will count the number of valid subarrays ending at the current index. As we iterate through the array, we handle three cases for each element. If the element is greater than right, it marks the end of a valid window, so we update last_invalid and reset valid_count to 0. If the element is less than left, it doesn't start a new valid subarray but extends the previous valid ones, so we simply add the current valid_count to count. Finally, if the element lies within the range, left, right, it contributes to new valid subarrays. Here, we calculate valid_count based on the distance from last_invalid and add it to the running total count. After iterating through the array, we return the value of count, which represents the total number of valid subarrays. The sliding window approach is what makes this algorithm efficient. By avoiding the naive method of checking all subarrays, we reduce the time complexity from O(n² to O(n). This is achieved by leveraging the position of the last invalid element and dynamically updating the count of valid subarrays at each step. It's also essential to consider edge cases. For example, if all elements in the array are less than left, there are no valid subarrays, so the result is 0. If all elements fall within the range, left, right, then every subarray is valid, and we can directly calculate the total using the formula n+1/2. On the other hand, if all elements exceed right, the result is 0 since no subarray is valid. The data structures used here are simple and efficient. We rely on a single traversal of the array and use constant space variables to track progress. Specifically, we use count to store the total number of valid subarrays, start to mark the beginning of the current valid window, last_invalid to track the most recent invalid element, and valid_count to calculate the contribution of the current element. This simplicity ensures that our solution is both time and space efficient. The time complexity is O(n), because we only traverse the array once, performing constant time operations at each step. The space complexity is O(1), since we don't use any additional data structures beyond a few variables. This makes the algorithm highly scalable for large input sizes. Let's walk through an example to see the algorithm in action. Consider the input array nums equals 2, 1, 4, 3, with left equals 2 and right equals 3. Initially, we set count to 0, start to 0, last_invalid to -1, and valid_count to 0. At index 0, the value is 2, which lies within 2, 3. This forms a valid subarray, so we calculate valid_count equals 0, -1, equals 1 and update count to 1. At index 1, the value is 1, which is less than left. It doesn't start a new valid subarray but extends the previous one, so we add valid_count, resulting in count equals 2. At index 2, the value is 4, which exceeds right. This invalidates all subarrays ending at or after this index, so we update last_invalid to 2 and reset valid_count to 0. At index 3, the value is 3, which is within 2, 3. We calculate valid_count equals 3 minus 2 is equal to 1 and update count to 3. The final count of valid subarrays is 3. The final answer for this example is 3. This means there are 3 contiguous subarrays where the maximum element lies within the range 2, 3. By using the sliding window approach, we efficiently determine the result in linear time, demonstrating the power of this optimized solution. This Python solution efficiently solves the problem of counting subarrays whose maximum value lies within a given range. We define a helper function count_subarrays, bound, that calculates the number of subarrays where all elements are less than or equal to a given bound. This function uses a sliding window technique. Whenever an element is within the bound, we extend the current subarray count, otherwise, we reset the count. The main function computes the result as the difference between subarrays with maximums bounded by right and those by left 1, effectively isolating the ones with maximums in left, right. This approach is linear in time complexity, O(n), making it optimal for the problem. Here, we have the Java implementation of the solution. The number subarray bounded max method calculates the number of subarrays where the maximum element lies within the given range, defined by left and right. To achieve this, we utilize a helper method called countSubarrays. This helper method computes the number of subarrays with a maximum value less than or equal to a specific bound. By subtracting the results of countSubarrays, nums, left 1, from countSubarrays, nums, right, we isolate the subarrays where the maximum value is strictly between left and right, inclusive. Next, let's look at the countSubarrays method itself. It iterates through the array, maintaining 2 variables, current, which tracks the length of valid subarrays ending at each index, and count, which accumulates the total number of valid subarrays. If the current element is less than or equal to the bound, we increment current and add its value to count. Otherwise, we reset current to 0, breaking the chain of valid subarrays. This efficient approach ensures that we consider all subarrays without explicitly generating them. Finally, in the main method, we test the solution with an example input. The array nums contains the elements 2, 1, 4, 3, and the range is defined by left equals 2 and right equals 3. Using the number subarray bounded max method, we calculate the number of valid subarrays and print the result. In this case, the output is 3, meaning there are 3 subarrays where the maximum element lies within the range 2, 3. This demonstrates how the implementation correctly handles the logic and efficiently computes the desired result using the helper method and subtraction approach. To solve this problem, we need to count the number of contiguous subarrays where the maximum element lies within the range left, right. The approach involves using a helper function called count_subarrays, bound. This function calculates the number of subarrays where all elements are less than or equal to a given bound. Once we have this count 4 bound equals right, we subtract the count 4 bound equals left 1 to exclude subarrays where the maximum is less than left. Let's start by executing count underscore subarrays with bound equals 3 for the input nums equals 2, 1, 4, 3. Initially, both count and current are set to 0. As we iterate through the array, when we encounter a number less than or equal to 3, we increment current by 1 and add it to count. If we encounter a number greater than 3, we reset current to 0. Applying this process, 2 and 1 increase the count to 3 for resets current, and 3 adds 1 more to make the total count equals 4. This value is returned from the function. Next, we calculate count underscore subarrays 4 bound equals left 1, which is 1. The process is the same, but now we are only considering subarrays where all elements are less than or equal to 1. Starting with count equals 0 and current equals 0, when we encounter 2, it exceeds 1, so current is reset. 1 is less than or equal to 1, so current is increment to 1 and added to count. The numbers 4 and 3 also exceed 1, so current remains 0. The result of this calculation is count equals 1. Subtracting these results, we find that the number of subarrays where the maximum is within 2, 3, is 4, 1 equals 3. Therefore, the output for this example is 3. For the second example, the input is nums equals 2, 9, 2, 5, 6, with left equals 2 and right equals 8. Starting with count underscore subarrays 4 bound equals 8, we initialize count and current to 0. As we iterate through the array, numbers less than or equal to 8 increment current, and numbers greater than 8 reset it. Specifically, 2 starts the count at 1, 9 resets current, 2 adds 1 again, 5 increases the count to 4, and 6 brings it to 7. The total count is 7, which is returned from the function. This gives us the number of subarrays where all elements are less than or equal to 8. Now, we calculate count underscore subarrays 4 bound equals left 1, which is 1. Here, we are looking for subarrays where all elements are less than or equal to 1. Iterating through the array, we see that all numbers exceed 1, so current is reset to 0 each time, and the count remains 0 throughout. The result of this calculation is count equals 0. Subtracting the results, we find that the number of subarrays where the maximum is within 2, 8, is 7, 0 equals 7. Hence, the output for this example is 7. In the third example, the input is nums equals 1, 2, 3, 4, with left equals 2 and right equals 4. Using the same process, we calculate count underscore subarrays right equals 4 to be 10 and count underscore subarrays left 1 is equal to 1 to be 1. Subtracting these, the result is 10, 1 equals 9. This gives us the final output for this example. To summarize, the key insight is that the helper function count underscore subarrays bound efficiently counts valid subarrays by summing the lengths of contiguous ranges where all elements are less than or equal to bound. By subtracting results for different bounds, we exclude subarrays where the maximum is outside the specified range. This method runs in O(n) time, making it scalable for large inputs. The final outputs are 3 for example 1, 7 for example 2, and 9 for example 3. Here, we are analyzing the time complexity of the solution, starting with the helper function count underscore subarrays. This function iterates through the array nums exactly once, performing constant time operations for each element. Specifically, it checks if the current element is within the given bound, updates a running count if the condition is met, or resets the count otherwise. Since these are all O(1) operations and the loop runs for all n elements, the time complexity of the helper function is O(n). Next, in the main function number subarray bounded max, we call this helper function twice, once for the right bound and once for left 1. Since each call is O(n), the total time complexity of the main function is O(n) plus O(n), which simplifies to O(n). This makes the solution very efficient from a time complexity standpoint. Now, let's look at the space complexity. The solution has a space complexity of O(1), because it does not use any additional data structures. Instead, it only maintains a small number of scalar variables. In the helper function count underscore subarrays, we use two variables, count and current, to track the running total and the current subarray count. Since these variables are scalars, their space usage is constant, or O(1). Similarly, the main function does not allocate any extra memory beyond what the helper function uses, so the overall space complexity remains O(1). This constant space usage is another key advantage of the optimized solution. Let's compare this optimized solution to a brute force approach. In the naive method, we would generate all possible subarrays of nums and check the maximum value of each subarray to see if it lies within the range, left, right. Generating all subarrays requires n² time since there are about n*(n+1/2 subarrays. Additionally, finding the maximum value of each subarray could take n in the worst case, leading to an overall time complexity of n³. On the other hand, the space complexity could reach n² if we explicitly store all subarrays. In comparison, the optimized solution avoids generating subarrays altogether and instead uses a single linear scan with a running count, reducing the time complexity to n and the space complexity to O(1). This demonstrates the efficiency gains of the optimized approach. Now let's consider the best, average, and worst-case scenarios for this optimized solution. In the best case, where all elements of nums are either less than or equal to right or greater than left 1, the algorithm still processes every element in the array exactly once, resulting in a time complexity of n. For the average case, the performance remains n, as the number of operations is directly proportional to the size of the array, regardless of how values are distributed. Even in the worst case, where the array alternates between values within and outside the bounds, the algorithm processes each element individually in one pass, maintaining the n time complexity. Mathematically, since the helper function performs a single pass with O(1) operations per element, its complexity is n. The main function calls the helper function twice, adding up to 2*(n), which simplifies to n. Since no additional data structures are used, the space complexity stays at O(1). This linear time complexity and constant space usage make the solution a highly efficient alternative to the brute force method. Here are some common mistakes to watch out for when solving this problem. First, not handling edge cases is a frequent issue. For instance, if the array is empty, contains only one element, or if all elements fall outside the bounds specified by left and right, it's easy to overlook these scenarios. Always include these edge cases in your test plan. Next, it's important to correctly interpret subarray boundaries. Subarrays where the maximum value exceeds right are invalid. Make sure your logic excludes them from the count. Another pitfall is relying on brute force methods. Generating all possible subarrays with nested loops leads to inefficiencies, especially for large arrays, as the time complexity can balloon to n² or n³. Instead, aim for optimized approaches like sliding windows. Additionally, be cautious about double counting subarrays when using sliding window or two-pointer techniques. Proper window management is key to avoiding this mistake. Finally, remember not to confuse the conditions related to left and right. Subarrays fully within the bounds and those partially touching the bounds should be handled with clear and distinct logic. Now, let's look at some interview insights that can help you approach this problem effectively. One of the most efficient techniques is the sliding window pattern. It allows you to dynamically adjust the window size while counting valid subarrays, making it a powerful tool for optimization. Another useful strategy is divide and conquer thinking. By separately counting subarrays that meet the equals right condition and subtracting those that fail left, you can simplify the problem into smaller, manageable pieces. When explaining your solution, highlight how you optimized the time complexity from n² to n by eliminating redundant computations. This demonstrates your ability to write efficient code. Lastly, make sure you can articulate how you handle the boundaries defined by left and right. Efficient boundary management ensures correctness, especially in edge cases, and is a detail interviewers often focus on. Finally, let's connect this problem to related challenges and alternative approaches. Some similar problems include LeetCode number 713, which involves finding subarrays where the product of elements is less than a given value. This also uses a sliding window technique but focuses on products rather than maximum values. Another example is LeetCode number 209, where the task is to find the smallest subarray that meets a sum condition. Similarly, LeetCode number 862 leverages sliding windows and prefix sums to address some constraints, while LeetCode number 53 is a classic problem that focuses on finding the maximum subarray sum, often solved using Cadon's algorithm. In terms of alternative approaches, prefix sums and differences can sometimes help calculate subarray properties, though they are less suited for this particular problem due to its focus on maximum values. The two-pointer approach, which sliding window builds upon, is another powerful tool when used effectively, requiring careful expansion and contraction of the window. Lastly, monotonic stacks are useful in problems that involve array maxima or minima, though for this problem, sliding window techniques are generally more intuitive and efficient. Great work! We've covered the problem, its solution, and key insights. Remember, mastering these techniques will make you more confident in tackling similar challenges. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!